When it comes to the replacement reactions, you're usually working with ionic compounds. In a single replacement reaction, you're starting with an element and it's interacting with a compound. What happens is that element kicks out its counterpart. So if element A is a metal, it's going to kick out the metal in the compound, and if element A is a nonmetal, it'll replace the nonmetal. And so to look at the pattern of the reaction and to be able to identify it, you're going to look for an element in the compound in the reactants, and then a new element and a new compound in the products. Now with double replacement reaction, everybody is switching partners. No one's being kicked out of a compound. And to recognize this, you're going to be starting with two ionic compounds, A and B plus C and D. And what happens is they switch partners to form two new compounds. And it's important to know and remember that when it comes to ionic compounds, two positives won't come together and two negatives won't come together because they repel. So the new compounds or the new combination has to involve a metal and the nonmetal component, um, and then the metal and the nonmetal component that are left over. So if we move on to the next slides here, it's going to give you a little bit more information about these replacements. So in single replacement, again, you have an element that's by itself that's kicking out an element in the compound and replacing it. So the element that's kicked out then becomes elemental form. And like I just said earlier, the element replaces the one like it. So the metal replaces the metal, the nonmetal replaces the nonmetal. There's something called an activity series to see if that element can kick out and replace its counterpart in the compound. If it cannot, then no reaction occurs. And actually, what we would write is NR, no reaction. So if you were asked to predict the products of a single replacement reaction, and you see that the element that is trying to replace something in a compound is lower on the activity series than the thing it's trying to replace. So here we have metals on one end and nonmetals, specifically the halogens, on the other. If the element that's trying to replace and get into the compound is not higher on that activity series, then the reaction will not happen. And we'll have an example of that in just a second. Now, when it comes to double replacement reactions, we don't have to consult the activity series because we're not trying to make something neutral and kicking it out. There's no changing of electrons that's happening. It's really just the ions floating around in a solution because they're all aqueous. The thing you have to remember with a double replacement reaction is that you have to have a precipitate at the end. So that's something that is either a solid, a liquid, or a gas as the product. In other words, not aqueous. Okay, and you would consult the solubility rules chart up here, and we'll use this in just a second in an example to determine if any of the ionic compounds that form are in fact not soluble in water, and so therefore will be the precipitate. Now, as far as gases and liquids are concerned, that's where you use your logic. So for instance, water is always a liquid, right? And then we have our gases like H2, Cl2, carbon dioxide. Those are all of our gases. So, you don't have to consult a solubility rules chart for them because they're not ionic compounds. So let's put some of these into practice with examples. So the first example is a single replacement reaction, and I know this because I have an element of copper reacting with a compound of zinc nitrate. Copper is my metal, and it's going to try to replace the metal in my zinc nitrate. So in order for that to happen, we're going to see if zinc is going to get kicked out by itself, and then copper is going to come in and now be in a compound with nitrate. But in order to really see if this reaction happens, we have to consult our activity series. So can copper replace zinc? Let's take a look. So I'm going to find copper on my thing here, and it is down here. There he is. And I need to find zinc now. Now remember, zinc is the one that's in the compound. Here's zinc. So zinc is in the compound. Copper is less reactive than zinc. It's weaker than zinc, okay? It's not going to be able to kick it out. So going back here, we're going to say that no reaction takes place because copper is lower on the activity series than zinc and won't be able to kick the zinc out of that stable compound that it's in. Remember, you're trying to break up a stable relationship here. That's not going to happen if you as an element are not better than the individual in that relationship already. Okay, so let's apply that logic to the second one. We have aluminum trying to kick out copper. And I know this because aluminum is a metal and copper is the metal. Okay, so sulfate's just kind of, doing its thing in this reaction. It's just kind of hanging out and seeing if it's going to get a new partner. So if you don't mind my drawings hanging out here for a second, if we consult this, we're going to find copper again. So copper is right here. And this time, aluminum is trying to replace the copper, right? So aluminum is higher on the activity series than copper. Aluminum is stronger than copper. Okay, so remember that aluminum is stronger than copper. So if we go back here, aluminum is trying to kick out copper, and since aluminum is stronger than copper, it's going to succeed in being able to break this apart and replace it. So copper is going to get kicked out. Copper is a metal now and is solid. It's neutral. Okay, it's no longer in the ionic compound, so it doesn't get kicked out as an ion. Elements are always neutral unless they've formed a relationship with something else to form that ionic bond. So that means that aluminum had to become an ion in this case by a transfer of electrons. And so now it is with sulfate. So aluminum forms a +3 and sulfate is a -2. So this would be the formula. And then of course you'd have to go back and balance everything, which I'm not going to do in this video, but you'll have to do. Okay. All right, moving on to sodium chloride and potassium nitrate. So I'm looking at this and I know that this is going to be a double replacement reaction. And that is because I have two compounds that I'm starting with. I have a sodium chloride ionic compound, a positive and a negative, and a potassium nitrate, a positive and a negative. So they're going to switch partners. The positive of one compound is going to go with the negative of the other. And then the positive of the one compound will go with the negative of the other. All right, now, in order for this to be a reaction that actually forms some kind of new product, one of these products has to be a precipitate. That means a solid, a liquid, a gas, anything but aqueous. Think about why that makes sense. If we're starting with two aqueous compounds, we basically have a beaker full of water with all of these ions that have disassociated and are floating around. If these both are also soluble in water, then we have the same beaker with literally the same ions floating around. Nothing new formed. They're all floating around. They're not floating around together or next to their partner. So it's really just, if these are both aqueous, you just have a beaker of literally the same ions. No chemical change happened. Okay, so I'm gonna have to clear all my drawings. Unfortunately, the way that this technology works right here to get over to the solubility rules without too much stuff being written on it. So when you're looking at the solubility rules, depending on what kind of chart you're looking at and how it's organized, you want to take a second and try to figure that out. So up top here, I see that these are my soluble compounds, right? And these are the things that can dissolve in water and will form an aqueous solution. So this is telling me that compounds containing nitrate are soluble and there are no exceptions. So notice over here, there's exceptions, right? Make sure that you're keeping those in mind. So if a compound contains nitrate, it's soluble, no exceptions. Also, this is down here is a polyatomic ion called acetate. Anything that contains acetate, always soluble, no exceptions. Now, these ions are usually soluble. If these ions are in the compound, they're usually soluble, but there are some exceptions. So what you want to do is look at your substances and check and see what you have and where it fits on this chart. Now, compounds containing sulfate ions, carbonate, phosphate, and hydroxide ions are usually not soluble in water, with some exceptions, obviously. Some things that you might want to just memorize because they will come up over and over and over again is always soluble with no exceptions is nitrate, and it's actually not in this chart. I just realized that. That's not good. All group 1 ions. So that's 1 on the periodic table. Hydrogen, lithium, sodium, potassium. I forget what comes after potassium. Cesium, maybe? I don't know. I'll have to check a periodic table. But in the periodic table, anything that's in group 1, if it is part of the ionic compound, that compound is soluble, no exceptions. So these are 2 things that you can memorize that'll make your life easier in this class, is if you remember that anything with a nitrate is soluble with absolutely no exceptions, and anything that has a group 1 metal in the compound is soluble with no exceptions, then you won't have to constantly be looking for this chart, okay? So I am going to go back to the slide that has our examples, and let's put this into play. We were looking at sodium chloride and potassium nitrate. Look, group 1, always soluble. Group 1 and nitrate, ooh, definitely always soluble. So if you think about it, potassium is group 1 and everything is always soluble with it, and nitrate is in a compound always makes it soluble. When they separate and form your new substances, so we've got NaNO3, right? Well, group 1 and nitrate always soluble. This is going to be aqueous. And that potassium with the chloride, potassium is a group 1A element. So this is always soluble. This is aqueous, absolutely no questions asked. Some compounds with chlorine are not soluble, but because it's with potassium, which is a group 1A, then that's it. They're both aqueous. So long story short, I have 2 aqueous compounds at the end. I started with 2 aqueous compounds in the beginning. There's absolutely no reaction here. Nothing happened. There was no change. Okay? So now we have to do the second one. You're probably guessing that this will have a chemical reaction, and you're right. So the sodium and chlorine and silver and nitrate, right? The positive goes with the negative. So we have sodium nitrate. Sodium is a group 1 element, which means that the compound that it's in will be soluble in water. And nitrate compounds are also always soluble in water. So I have 2 things that make this aqueous. I know that's aqueous off the bat. So now I'm going to have silver and chlorine together for silver chloride. And I don't know, a lot of chloride compounds like sodium chloride are soluble, but let's check with silver. So let's go to our solubility rules over here. I have my chlorine, so I'm going to look and see. Okay, silver, so it looks like this is all set by anion. So it looks like we're looking at all the negative ions, which is why the group 1 isn't listed, which makes sense. So I'm going to look for chlorine, right? Because I have silver chloride is what I want to find. So here's my chlorine. And it's saying that anything that has chlorine as an ion in it is soluble, except if it's with these things. If it's with silver, mercury, or lead, and oh, it's with silver. Okay, so compounds that have chlorine in them are soluble in water, except when it's with these 3 metals, and that is what we have in our situation. So what I can do is go back to my reaction here and say that this reaction will happen because a precipitate's going to form. Sodium nitrate is going to be aqueous. That's fine. Those will still be ions. There are spectator ions. But when silver bumps into the chlorine ions in that solution, they're going to form a bond that water can't separate. And that's going to be our precipitate. That's going to be our solid. So that's how you're going to use solubility rules and also the activity series to be able to know what state of matter substances are in, and also if those reactions are going to take place at all.